everyone. Integrals day number 2. Nope, day number 4. Let's get started. We're going to talk about the proof of convergence. Today's topic specifically is the comparison test. Alright, let's get started. Alright, so the comparison test for improper integrals. Alright, so here is the short on this. Let's say you want to determine whether or not an improper integral has a finite area, right? If an improper integral has a finite area, or the answer comes out to be a number, a countable number, that means that that integral converges, right? If it doesn't, if it comes out to be some form of infinity, then that means it diverges. So let's say that you have a function, for example, this red one here, e to the negative x squared. All right, that is just nasty to try to integrate. I don't want to have to integrate it. And because of that, I'm not going to be able to find an exact answer for the area under the curve if it even converges at all. So what we do is we use this thing called the comparison test. And the comparison test will have 3 steps. Okay, the first step is we're going to write out an inequality. All right, we want to find a function. In this case, the function e to the negative x. All right, e to the negative x is always larger than e to the negative x squared on this interval from 1 to infinity. All right. Therefore, the area under e to the negative x will always be greater than e to the negative x squared, and those values will always be positive. Okay, so if we can find out, an easier function to integrate on that improper set of values, if we can show that this thing right here converges, right? If this converges, then that would force this to converge. Right? That would force that lower function to converge. But if this diverges, then we don't know. Right? It could converge, or it could also diverge. So we want to pick functions, and that'll be part of our work today. We want to pick functions here that we know converge. Because if that's true, then we're guaranteed that this inner function will also converge. So our second step is to take and determine on that same interval, does our chosen function converge? Okay, and we can go ahead and do that, right? So I'll do that on the next page, right? Actually, I'll give you the answer right now. It does converge. It converges to 1 over e. Okay, and then our third step is a therefore statement. So we would say, therefore, since 0 is less than e to the negative x squared, which is always less than e to the negative x on this interval from 1 to infinity, and the integral from 1 to infinity of e to the negative x dx converges, then the integral from 1 to infinity of e to the negative x squared dx must also converge by the comparison test. Okay, now we don't know anything about what this converges to, but we sure as heck know it will be less than 1 over e. All right, so it's not we're not getting an answer like a numerical answer. We're answering this question. Does it converge, or does it diverge? All right, that's our goal for today. Let's keep going. All right, we basically did this. So I'm going to skip this slide here. I didn't do the integration for this piece, but that's something maybe you can do on your own using your skills in improper integration at this point. Okay, so this slide is actually really important. I want to talk about this for a moment. I'm going to pick g of x functions that are either larger or smaller than f of x. So f of x, this function here, is our unknown. All right, so on the last slide, my known function, my g of x function, all right, this one was e to the negative x. That was a known integratable function, right? And I showed that converged. So my unknown function was this function e to the negative x squared. Okay, another way that you can go about this is to pick smaller functions. Now, why would I pick a smaller function? Well, I could pick a smaller function. For example, I don't know, I'm just going to throw this in there and go with it, but I'm not going to come up with a specific example. Let's say that my known function, right, my known function is smaller than the other function. Well, if this converges, that doesn't tell me a whole lot about this. It could converge, but it's possible it doesn't. But what if this diverges? Well, if a smaller function diverges, then that forces this to diverge as well. So there's some experience that comes into this, as well as, can you look at a function and say, I think that might not be convergent. That integral might not be convergent. You'll have that skill at least part of the way figured out by the end of today using what you're going to learn next. Okay, so now here comes the hard step, right? And actually it's not that bad at all. How do I pick functions? Right? I think that this function here, I think the area under that curve is convergent. Okay, well, step one is to come up with what that other function is. Okay, so I've got square root of x to the fourth plus 2x. Okay, so the best way to do this is if you have a rational function like this one, get rid of anything that isn't your highest power of that polynomial. Right, and what would that reduce to? What would 1 over the square root of x to the fourth reduce to? Well, it would reduce to 1 over x squared. Okay, so if I had all of this here, a larger number, especially when we go from 1 to infinity, a larger number in the denominator will actually make that number, that quantity, when you take 1 divided by it, smaller than this. Therefore, 1 over x squared would be greater than 1 over the square root of x to the fourth plus 2x. All right, and then we'd go ahead and we'd integrate this from 1 to infinity. Integrate the easy one. And then write your therefore statement. Okay, so over here, sine x, that's just going to oscillate, right, between negative 1 and 1. So it's not going to have a whole lot of effect as x goes to infinity. X squared won't have as large of an effect as x to the fourth will. And again, I'm left with 4x squared over x to the fourth, which reduces to 4 over x squared. Now, I would use that as my function, my upper function, right? So I'd have, all of this crazy stuff here, x to the fourth plus x squared plus sine x is going to be less than 4 over x squared. I'd integrate from 2 to infinity of 4 over x squared dx, and hopefully what I come up with is some finite number. Right, then I can say that said integral here is convergent using the comparison test. So let's put this to work here in a moment. Okay, so this slide is leading us into something really cool, which will give us a nice little shortcut here. Basically, it's saying anything of this form, right, where I have integral from 1 to infinity of 1 over x to some number. So 1 over x to the first, or 1 over x to the second, etc., where p is some real number. Okay. All right, so what is it telling us? It's actually determining for us, what values for P will make this convergent or divergent. And the proof is shown here as well as on the next page, so I'll go there. Proof continues here. What's the bottom line, Mr. Ludd? The bottom line is this integral will converge as long as P is greater than 1. So now we're going to call this the P series. Right? We're going to call this P series. So now if you see this integral 1 to infinity of, I don't know, 1 over x to the 3 halves. Is 3 halves greater than 1? Yes, convergent. This is powerful, right? Okay, integral from 1 to infinity of x to the negative 7 dx by P series, convergent. Okay, what about the integral from 1 to infinity of x to the negative 3/4? Well, when I put it in this form, 3/4 is not greater than 1, divergent. Okay, that's actually really powerful. It saves us the time of integrating. Okay, so I don't need to actually work through and integrate necessarily if I know it's a P-series function. Now, you won't always get a P-series function, so it won't always be that convenient, but in some cases it is. I speak numbers normally, not words. Okay, I want to go back a slide. Well, actually, I'll do one of these, and then I'll add a slide and do the one I really wanted to work through. Okay, so let's do step 1 here. Step 1 here, we want this function, I'm not going to write it out, to be less than something. I'm going to ignore, and reduce. Looks to me like I'll get 1 over 2x to the 4th. Part 2, integral from 1 to infinity, I'm going to pull that 1/2 out, so that'll be 1 over x to the 4th dx. Is that going to converge? Yes, that'll be convergent by P series. Okay, so step number 3 is my therefore statement. Therefore, since, and then I just state step number 1. I'm not going to write out the function in the middle, but you would need to. That would be less than 1 over 2x to the 4th for all values from 1 to infinity. Then the integral from 1, and since the integral from 1 to infinity of 1 over x to the 4th dx is convergent. I'm not writing very well. You need to do a lot better job keeping this clean. Then the original integral, I'm writing original. You have to write it all out. I get paid a lot of money, you don't. Okay, then the original will be convergent by the comparison test. Awesome. Let's just pick a function on this one. Okay, step 1. Oh boy, let's see here. This thing. Goodness. Oh, I like it. Okay, I like that this is a -1 here, because what I can do is this for sure is going to be greater than. So I can say in all cases that this is true, right? And so I'm going to strip away this in the denominator as well and just reduce this. All right, so I'm going to be reducing this. So x squared, I'll write this one out, over the square root of x to the 7th plus 1 will always be less than, on this interval from 2 to infinity, will always be less than 1 over x to the 5th. Ooh, not x to the 5th. Wait a minute. I forgot a square root there. Okay, so this is really x to the 7 halves. All right? So x to the 2nd is x to the 4 halves. So x to the 4 halves over x to the 7 halves is x to the 3/2. Looky there, p series. So in part 2, I know that this is true. By p series, it looks like this is going to be pleasant. Okay, that is a convergent p series. In step 3, you would go ahead and write your therefore statement. All right, so I would like to just kind of go off the cuff here and determine whether the following is convergent or divergent. Okay, my inkling when I look at this is that this is divergent. Personally, I look at it and I think divergent. And you might be saying, well, why? Because it looks kind of like this. Right? It looks kind of like that. And that's a divergent p series. Okay, so I want to do a quick comparison here and talk for just a moment. Okay, so square root of x minus 1. How does that compare to the square root of x? Would it be greater or less? Well, it'd obviously be less. But then how does this compare to this? Well, it's going to be greater. It's just like saying this. Is 7 greater than or less than 8? Well, it's less. But how about 1/7? How does that compare to 1/8? Well, it's greater. Okay, so what does that mean for my comparison test? Well, that means that I know a function that's divergent that's less than my unknown function. So if I can show in step 2 that the integral of this on that interval from 2 to infinity is divergent, which it is by p series. So the p series tells me in this case that this is divergent. Then I can write a therefore statement in step 3. So here's my therefore statement. Since 1 over the square root of x minus 1 is greater than 1 over square root of x, which is greater than 0 for this interval from 2 to infinity, and this is a divergent p series, then from 2 to infinity of 1 over square root of x minus 1 dx must also diverge by the comparison test. So there you have it, double lightsabers. That's an example. Whoa, wow, that's crazy. That's an example of using the comparison test to prove that an unknown function and the area under its curve is divergent. All right, guys, I think I might do one more homework question here. Let's jump into it. Okay, sometimes your test for convergence doesn't need the comparison test. So one of these 4 doesn't need the comparison test. I want you to take, I don't know, a minute or 2 and look at them and see which one would not need the comparison test. The one that actually does not need the comparison test is C. Why? Because it uses u substitution. So u in this case is natural log of x. Du is 1 over x dx. So don't lose track of the fact that you still have that at your disposal. All right, this would just be u du, right, which would be u squared over 2 on this interval from 1 to infinity. U obviously is natural log of x. And you would take that from 1 to b, and you'd do your improper integration work from there. All right, guys, this is good stuff. Comparison test is not going away. We're going to be using it throughout probably the next 3 to 4 weeks, maybe even longer. So know it, love it. Peace out. See you next time.